Okay. So the title of this work is the Investigating Light Emission Efficiency of metacomplex structure. Here we use tungsten metacomplex, and we are trying to analyze with different bipyridine. So the main objective, like why we are doing this work, because we are trying to see the behavior of photolysis in transition metal complexes. Especially the difficulty lies in the understanding and controlling the electronic transition and the relaxation processes that follow photo excitation, uh, which is important for the development or for the development, and also if we want to use those things for the optoelectronic property and biomedical engineering, we need to improve uh, the model. The m- main challenge, I believe, that it's when we use different ligand and their bonding with the central metal affect the energy level and consequently the absorption and emission spectra. Um, the hypothesis underlying this research is that the formation of tungsten and nitrogen bonds um, alerts the electronic structure of the tungsten hexacarbonyl complex in a such way that it could enhance the photolysis property. By formation of the bonding between tungsten and nitrogen, the band gap is reduced and potentially leading to more efficient absorption and emission processes. The creation of a new energy state with reduced band gaps. So this could result in the materials with improved the performance characteristics, and we are able to use for different application. So here I summarize the different objectives. The objectives of our work, that we first want to investigate the electronic properties of tungsten hexacarbonyl complex and understand how the formation of tungsten and nitrogen bond influence their photolysis properties. And also that things I already said, that we want to investigate, or I use examine, investigate the effect of the ligand modification on the band gap of tungsten complexes with bipyridine, how these changes correlate with absorption and emission. And also we analyze the excited state dynamic, and we are doing photoluminescence study to see their behavior. Okay. And also using the ab initio electronic structure and Redfield theory, we are trying to see the we are doing non-dynamic calculation and try to predict the electronic transition and the relaxation processes. So the main objective is that to bridge the gap between fundamental understanding and practical application, paving the way for innovations in light-based technology. Um, so the main reason for doing this, sorry, making this video is that, Professor, I want to uh discuss with you these things, and I was thinking that I think that you are so busy, and it's good idea to send you this video. Then, and if you watch this one, after that we can discuss more, and you can tell me how to improve this um, slides, and also what kind of things I need to add, or what kind of things I don't need to add. Just please let me know. So yes, and Here, this is the models we used. We use 6 different models and try to uh, see that which one shows the better photoluminescence properties. And for doing our calculation, we use a DFT calculation, and we use a PBE is zero functional. And our calculation divided in two parts. First, we did ground state calculation. In the ground state, we did density of state and absorption spectra. And after that, we did dynamic calculation. Then one call we introduced as a non-adiabatic dynamic calculation. So, Professor, I'm not explaining these things, but if after listening and this video, uh, if you give me some time, then we can discuss these things. Okay. So the thing what I am able to understand that when there is no or bipyridine inside the metal complex structure, then band gap is higher, and after that when we add the bipyridine, band gaps of the structure started reduce, and the formation of the tungsten and nitrogen bond also reduce the band gap of the structure. Okay. Then absorption spectra. So for the uh, absorption spectra, that things actually what we can say that um, here we actually compare the absorption spectra for all metallic complex structure, and we are able to see that uh, this blue peak, that one actually uh, that one is tungsten 3 bipyridine, and there is a double bond create between tungsten and nitrogen. So this model absorption spectra, we are able to see that it's shift uh, toward the lower range, and which actually indicate these um, metal to ligand charge transfer, and which is consisting with the formation of the bond, like because there is a bond creation happen between tungsten and nitrogen. That's why that absorption peak shifted in the left side, lower range, lower transition range, and that range is in the near infrared range. So only that model tungsten 3 bipyridine double bond, that one we are able to see that absorption peak in the near infrared range, whether are most of them like only this region, then this area, most of the peaks are in UV range. Only few of them uh, and they are like tungsten with 3 bipyridine with one bond, and also double bond. Those structure are in a visible UV range. Yes. So by comparing this structure spectra of the all complexes, we can understand that ligand we can understand that because of the formation of the bond, absorb an extended absorption happened into the NIR region, as we observe in some of the modified points towards successfully uh, introduce the MLCT states, means metal to ligand charge transfer step. So I think it is important to note that the direction of the charge transfer has significant implication for the physical properties of the material in the context of our study. The uh, formation of the bond between tungsten and nitrogen enhance the metal to ligand charge transfers, which can lead to improve the performance in application where light absorption and efficient charge separation are important. Then the next slides is this one. Then we are moving to the non-adiabatic dynamic calculation. Here here what we can observe that the left figure has for tungsten 3 bipyridine without any bond between tungsten and nitrogen. The middle one is the tungsten 3 bipyridine with one bond between tungsten and nitrogen, and this one, the third model, and that one is has double bond between tungsten and nitrogen. So initially, we from the charge orbital pair orbital, we are able to see that charge transfer happens when there is no bond between uh, tungsten and nitrogen. Charge transfers happen from ligand to ligand, and when there is bond creation, like formation of bond between tungsten and nitrogen, that one started like the middle one, we it's clearly visible that this transfer happened from the metal to ligand structure, and this transfer also similar pattern we are able to see when there is a formation of the double bond. And this suggests that after excitation, electron relax faster than holes, and also it emphasizes that that when electron relax faster than holes, that charge transfer happen from the metal to ligand structure when there is a double bond or one bond between tungsten and nitrogen. Then after that, because we want to Okay, so here is the dynamic of excitation for the metal complex structure. Here we compare the excitation and emission result for the model, the tungsten 3 bipyridate. And these slides actually, from these slides, we can understand that excitation and emission or dynamic of the tungsten hexacarbonyl complex, particularly how the addition of bipyridine ligands and the formation of bond between tungsten and nitrogen bonds affects the excitation and emission behavior. So here, this one I just wrote these things because sometimes I forget. That's why. But in the main slide, when I will present this one, I will remove those type of stuff. So for the excitation and emission, we use this equation, and so uh, as you can we can see that on the left side we have the excitation process, and the middle one for the emission, and the last one for integrated. uh, so left side excitation graph for all three models, and middle one for emission, and the last one integrated emission spectrograph, that one for the all three models. Okay, so here as we can see that when there is no bond, um, we when we excite the system, it excite up to 4 electron volt, and after that it's um, uh, here we can see that it's a energy drop, or we use the word energy cascade, uh, near 3.5 electron volt. But when there is a one bond formation between one like tungsten and nitrogen, that is one bond, though we use same initial excitation, that one is 4 electron volt, but uh, energy cascade, um, that one is higher compared to, sorry, it's dropped, uh, it's around 1.5, around 1 electron volt, or 1.2 or something like that. So here we can see that, and also we can see from the emission, and that here the bright transition near the almost 0 electron volt, and uh, this that energy cascade That one we can say that it's emit energy, quantum energy. That one is 1 electron volt, and that one we can say it's emit energy near infrared range. So that one also proved uh, like it's we can compare these things with the absorption spectra, that when the we have formation of the bond, then absorption spectra we are able to see in the lower transition energy region, and also uh, when we excite the system we are able to see that energy cascade from 4 electron volt to 1 electron volt. And also from the integrated emission spectrograph we are able to see that in here we cannot see any emission spectra peaks here, but when there is a bond between tungsten and nitrogen, that one creates several peaks here, and also when we have a double bond we can see these peaks. So yes, these are the things. If we focus on like we focus on the right side again, we can see that um, emission process, uh, that one tungsten 3 bipyridine complex without a bond, and we observe some electronic transition. Yes, that one I explained already here. So in conclusion, what I can say that the formation of tungsten and nitrogen bonds in this complex structure, metal complex structure, uh, leads to additional electronic transition. That one we observed in the relaxation dynamics, and this has a profound impact on the emission characteristics of the complexes, which is essential for the application in the optoelectronic device. And what is the next? The another one. This one, the we are saying that for our result for this whole study, this one we are saying the most important result. So here we are trying to show the photoluminescence efficiency of different tungsten models with the varying the bipyridine. The key indicator, actually we are trying to focus on the photoluminescence quantum yield, which serves as a benchmark for the materials potential in the light emitting application. So when we look at the result table, the PLQY, photoluminescence quantum yield, that one for different models it gives us different values obviously, and for like the one tungsten 3 bipyridine with double bond, it is particularly it shows that it's a PLQY, it's 0.3650, so it's 36.5%, which is highlighted in the figure. This fellow actually suggested that the more than one third of the absorbed light is successfully re-emitted as a luminescence. which is substantial efficiency level in this constant in this context, sorry. And when we see the only tungsten, this one is like we are using here as a reference structure. So here PLQY it's 0.9926, so that one is almost 100%. That would mean that every absorbed photon result in the emission of photon, which is an ideal scenario. So in practice, actually achieving high PLQY values is challenging due to various non-radiative process that can happens in the photoluminescence when we did. Therefore, the observed PLQY, that one tungsten 3 by with a double bond, that one we can consider as a potential candidate for efficient light emitting application. So another fact is that in the model has higher PLQI compared to the other. Study indicates that the modification into its ligand structure and the resulting electronic transition are conduct to enhance the photoluminescence, and this opens up a pathway for designing a new material with tailored properties for specific optoelectronic application. So in conclusion, our result underscore the importance of molecular structure in determining the photoluminescent properties of transition metal complex, and it's a highlight that the PLQY values not only reflect the material's current performance but also a guide for future modification to optimize light emission. And let's go to the conclusion slides. So the conclusion here, I wrote that we are doing the non-inhibiting dynamic calculation, which shows that charge transfer happens from the metal to ligand structure, and the formation of the bonds between tungsten and nitrogen indicates an emission range from UV to near infrared range. And the during the metal to ligand structure, so a metal to ligand charge transfer, an electron is excited from metal central orbital to an orbital that is largely centered on the ligand, and this result actually in uh, shows we are able to observe from the electronic density that has moved from the metal to the ligand and effectively transferred a negative charge to the ligand. It's charge transfer from metal to ligand. The photoluminescence of the tungsten, um, tungsten, it's not hexacarbonyl. Tungsten and hexacarbonyl 3 bipyridine with double bond. That one shows a higher intensity compared to the others, and it's a PLQY. A photonemesis quantum yield value is 36.50%, and these things these values we are able to see because of the formation of the bond between tungsten and nitrogen, which suggests that the complex is quite efficient at emitting light upon photo excitation. So the I hope, professor, you will listen in these things. I was trying to explain the slides, but I don't know because sometimes I'm trying to think that what should I say, and and let me know when you have time after hearing this, after listening this video. Then please let me know when you have time, then we can discuss and improve these slides. Thank you, and sorry for this horrible explanation. I tried, uh, mm, not level based, but I tried from my sides, but I need your help. Thank you, Professor.